Hi Bobcats! In this video we're going to take a look at valence electrons, which play a key role in predicting how an atom will react and form bonds with another atom. Our objectives are to define what valence electrons are, to take a look at an electron configuration and identify which electrons are the valence electrons, and then to just look at the atom's position in the periodic table and quickly determine what the number of valence electrons is. Valence electrons are important because they participate in the bonding that an atom will be involved in, which means that they're involved in chemical reactions. The definition of valence electrons is all of the electrons in the highest numbered shell. And keep in mind that they may be distributed across more than one subshell, such as the 2s and the 2p. Let's take a look at the valence electrons for these three elements. I've written out both the full electron configuration and the noble gas shortcut electron configuration. So if we look at barium and we look at its full electron configuration, we want to find the highest numbered shell. Well, I'm seeing shells 1, 2, 3, 4, 5, and 6. So the highest number that I'm seeing is 6, and there is only a single subshell. It's the 6s2, and since there are 2 electrons in that subshell, we have 2 valence electrons. If we look at the noble gas shortcut, it says xenon 6s2, and those 2 valence electrons are the only ones showing. That's one of the reasons that we do the noble gas shortcut, is to hide the electrons that don't really participate in bonding and emphasize the ones that are available for bonding. If we look at oxygen, in its full electron configuration, I'm seeing the first and second shells. So the second shell is right here with the 2p4, but it's also showing here with the 2s2. So we have 2 plus 4, which is equal to 6 valence electrons. And if we look at the noble gas shortcut, those are the only electrons showing. So once again, it's showing that we have 6 valence electrons. For cobalt, we're seeing the first, second, third, and fourth shells. Notice that the fourth shell is kind of hidden here between the 3p and the 3d. So there are 2 electrons in the valence shell, and so a grand total here of 2. And if we look at the noble gas shortcut version, we will see the 4s2 right there. So once again, 2 valence electrons. In a face-to-face class at this point, I'd be asking students to look at all of the various atoms that we had written electron configurations for, and then to tell me what atom they found and how many valence electrons it would have. So we would start kind of filling in the periodic table like this. There might be a 1 here and a 2 here, and maybe a 5 here, and 8 over here, a 2 here, maybe get a 2 there, maybe a 3 over here. So anyway, we would continue on this pattern for a while, and it would pretty quickly become apparent that there's a strong trend between the atom's position in the periodic table and how many valence electrons it has. For instance, everybody over here in group number 1 is going to end up with a single valence electron. So in group number 1, we'll find 1 valence electron. And in group number 2, we need to add helium. Remember, for electron configuration purposes only, we move helium over to the left-hand side to group number 2. And everybody in group number 2 ends up having 2 valence electrons. And I'm going to skip this middle block, the D block, for the moment. If we head back over to the P block, the boron family, all of those elements have 3 valence electrons. The carbon family all have 4. The nitrogen family have 5. The oxygen family will have 6. The fluorine family 7. And then once we have moved helium over to the other side, the remaining noble gases all have 8. You can determine that by looking at the last digit of the group number. For instance, the oxygen family, which has 6 valence electrons, is in group number 16. So we take the last digit of the group number for the S block and the P block, and that will tell us how many valence electrons there are. So for the S and P block, we're going to look at the last digit of the group number. The D block, though, gets a little weird because those S electrons are buried underneath the D electrons at the end of their electron configuration, and the S electrons are always one shell higher than the Ds. So no matter which D block atom we look at, we're going to come up with 2 valence electrons. So all of those D block electrons are going to have 2 valence electrons. Please take a moment and figure out how many valence electrons are in each of these 3 elements, and just pause the video while you're doing that. All right, let's see how many valence electrons you came up with. Neon is a noble gas, which is in group number 18. That's over in the P block, so we're going to take the last digit of the group number, and it has 8 valence electrons. Calcium is in group number 2, which is in the S block. So if we take the last digit of the group number, that's a 2. So it has 2 valence electrons. Gold is in the D block. Every element in the D block has 2 valence electrons. To wrap up this section, we wanted to define valence electrons, identify the valence electrons in an electron configuration, and then to find the number of valence electrons in an element from its position in the periodic table.